It is 1 o'clock, October 17th. We can now begin class. So it would seem we have 3 or 4 people here. Last session, I ended off by giving each of you homework. If you can, could we start the lesson by any of you sharing your screen of your homework so we can go over it?
Me, sir.
Thank you, Mr. Nathan. Would you please share your screen?
No.
Okay. Mr. Nathan, if you could hold the camera on your homework for a little while. So let's start off with what the instructions for the homework were. You had to find any shape in your house. Make any area you want. Draw your measurements to justify the area. Or rather, I should say label. And take find the area of a triangle, base 4 and height 7. Find how many triangles would fit into your shape. Okay, let's start first with our triangle. Mr. Nathan, what is the area of the triangle that we were given?
The area of the triangle.
Yes.
Wait. 56.
So you
No,
said
sorry, I mean 14.
14. Very good. Goodness. So the area of a triangle is, could you tell me, Mr. Nathan?
Half base times height.
Very good. Half base times height. So you took what you were given, the measurements, and you plugged them in. Excuse me. And you found your area to be 14. Thank you, Mr. Nathan. So now that we have the area of our triangle, what is your shape, Mr. Nathan?
A rectangle.
Okay, Mr. Nathan, your video is breaking up a little bit. So from now on, please describe your work instead of sharing your screen, all right?
Okay, sir. The area of my rectangle is 8 is 56 and the length.
So your area is 56. So Mr.
And my
Nathan,
length and width is
yes,
8 and 7.
very good. So your length and width is 8 and 7. Because the area of a rectangle is length times width. So now that you have the area of your rectangle and you have the area of your triangle, you labeled all your measurements. Now you need to find how many triangles fit into your area. Mr. Nathan, how would you do this?
I divided, sir. I
Very
divide
good.
14 and 56.
Very good. So what was your what was on top and on bottom?
56 was on top and 14 was on bottom.
Very good. 56 on top, 14 on bottom. What did this come out to, Mr. Nathan?
The answer for that is 4.
Very good. So what does this 4 mean? Describe to us what this 4 means.
The 4 means that 4 triangles can fit in a rectangle, which has the area of 56.
Very good. Thank you, Mr. Nathan. You did your,
You're welcome, sir.
thank you. All of your work was correct. If this was a great assignment, you would get full marks. The only critique I would make is that your description was slightly off. The point of this assignment is that when you compare the areas, instead of saying 4 triangles, it would be the 4 triangles worth of area. So what I mean is that even if the areas are proper, the way you have them, it doesn't necessarily mean you can perfectly fit the triangles into the rectangle and make the rectangle shape. It means that the amount of area of the triangles are equal to the amount of area of the rectangle. This would be like melting cookie dough and putting it into a cookie cutter. That's how you get the shape out. You need a certain amount of material, and that material fills up a certain amount of area. Very good, Mr. Nathan. Mr. Aryan, if you're not having difficulty, would you like to describe your shapes?
Sir, may I present?
Yes, you may, Miss Ariel.
Sir, I did mine a bit differenter.
That's perfectly fine.
I drew, my object is, I don't know if you can see it, sir. What I did.
Okay. It's a little blurry, Miss. Oh, there it is. Okay, so you have a set of blocks. So you have a flash drive.
Yes, sir.
So this is the shape of your flash drive. What was your area?
My area of the shape is 3.3. The base is 3.3. And the
Your area was 3.3?
No, sir. My base was 3.3 cm and my height was 5.7 cm.
Your height was 3.7 cm? Miss Ariel, it seems that there's a little bit of difficulty with the internet connection. Could you type it in the chat?
Okay, sir.
I would say my internet is a little unstable. Okay, base of 3.3 centimeters and a height of 3.7 centimeters. I would like to start by saying I thank you a lot for trying to go the extra mile, because not only do you have units with your measurements, but you also decided to make your you decided to label your measurement with fraction, with decimals.
Okay, sir.
So your height is 5.7. So what was your area?
My area is 9.405 cm.
9.405.
Yes, sir. cm.
Okay. cm. Would it be cm or would it be cm squared?
cm square, sir.
Very good. So how did you label your measurements for your flash drive?
I put area of shape, which is base equals 3.3 cm.
Yes.
And then I put area shape, that is height, equals 5.7 cm. And then area height times breadth divided by 2 equals 5.7.3.3 divided by 2 equals 9.405 cm square.
Okay, so it sounds like you took the area of a triangle
Yes, sir.
and you found it to be 5.5 1/3 over 2.
Yes, sir.
Okay, so uh,
Height by 2.
I'm so, so that'd be 15 over 6, I believe. No, yeah, no, 16 over 6. So you found the area of a triangle,
Yes, sir.
which I believe will come out to be 16 over 6. What was this triangle for?
Sir, I'm not sure.
That's perfectly fine. Could you please share your screen again? Let's try it one more time.
Um,
Oh, 5.733.
yes, sir.
I'm sorry, I misheard you. 5.7. Goodness. So 5.73, which is 57 and a third over. Okay. I'm not quite sure if your calculation is correct. 5.733 over 2. Let me take out my calculator. Okay. 5.733 over 2 comes out to 2. I'm gonna erase this little model for a second. So, okay, height times base over. Oh, okay, I thought. Oh, okay, I see. You were correct. I simply read your math a little wrong. When you write your decimals in the future, write them a little lower, because when you have a dot that's in the middle, it looks like you're saying to multiply it. So make sure you write it just a little lower so that we can tell it's a decimal. Good?
Yes, sir.
Okay, so you found the area of this triangle,
Yes.
which is 9.405 centimeters squared. Okay, so we had this triangle. And this is the area of the little triangle you had. Okay. So let's say this is your flash drive. I like how you drew. I like how you drew your flash drive with the little triangles in it.
Thank you, sir.
So, as it is right now, we can't really tell much about the flash drive, just from the way we drew it, and the measurements aren't exactly clear. However, there is something that we can do. Look at with the way that you drew your flash drive. You drew it into 6 squares here, and you have 4 smaller squares here. And then you drew little triangles in the flash drive. And then little triangles inside here. What we can do, and say, is that we can say that the base and our height is the base and our height of each of these little triangles. Instead of saying for the whole thing. And we'll say that this square here is the same as these 6 squares here. We'll just say it for the to make it easier. So let's say our height and our base, which we described here, is one of these triangles, and we found the area of one of these triangles. So as we have it here, there are 7 boxes, and in each box there are 2 triangles. So how many of these triangles will be in this model?
Sir, when I counted my triangles, I end up with 20 of them, sir. There are 20 triangles.
Okay. So the way you have it, so we have the same amount of triangles in the body here. So that is 12 here. You said in yours you have 20 triangles, so you have 8 triangles in this little box. In this box that we have in our model here, we have 2 triangles instead, just to make it a little simpler. So instead of saying 20 triangles, we'll just have 14 triangles so that all these triangles can be the same. Does that make sense?
Yes, sir.
So we have 14 triangles in this whole model. So that means if we have 14 triangles in the whole model and we want to find the model's area, what can we do with the area we have of one of the triangles?
Sir, could we divide them by 2?
Not quite. So we want to find the area of the whole model, and we know that the whole model consists of 14 triangles. So we have the area of one triangle. So if there are 14 triangles in the model, what can we do with this area to find the area of the whole model? Here, let me, oh. Okay. So we redid the model. So there are 14 triangles in this whole model, and we want to find the area of the whole model. If we have the area of one of the triangles, and there are 14 triangles in the whole model, how can we find the whole area with the area that we have of one of the triangles?
Sir, I think we can divide it by 14.
You're very close. We want to multiply it by 14.
Okay, sir.
Very good. So it would be like saying if if I have 2 hands and I want to find out how many fingers are on both my hands, but we know how many fingers are on one hand, then to find how many fingers I have on both of my hands, we just multiply the number of fingers on one hand times 2. It's the same idea here. If we have the area of 1 and we want to find out how much area is 14 of them, we multiply the one area we have by 14. And that will come out to, okay. So that will come out to 131.67 centimeters squared. Let me rewrite it. Perfect. So this is the area of the whole model, the whole flash drive. Thank you, Miss Ariel. So now that we have pretty much everything, we labeled our measurements for our model, and we said what our area is in total. Now we just need to find out how many of these triangles we need to build this model. Now, I'd like to start out by saying that in the original homework, we did not say that the original triangle had units. But because we have units here, we can just say that it is 14 centimeters squared for the units. So now that we have the area of the whole flash drive, Miss Ariel, how can we tell how many of these triangles we need to come up with this area?
So I'm not sure.
That's perfectly fine, Miss Ariel. So what we do is kind of like what we did here, but in reverse. In this case, we knew how much area was one triangle. So we had the area of 1, and we had the number of triangles, so we could find the total area. That's how we did this. Now we have the area of one triangle, which is this, and we have the area total. So what's missing? Just the number of triangles. So that means we are solving for the number of triangles we need to find. That's the whole homework. So to find it, we can isolate the number by saying that the number of triangles is equal to the area of the total, which is the area that we found, over the area of one, which is what we have here. So that means that our answer will be equal to the total area we found, 131.67 centimeters squared, over 14 centimeters x squared. Does this make sense, Miss Ariel?
Yes, sir.
Very good. So I'll use my calculator, divided by 14. Now, because we're dividing and we have our units, the centimeter square on top and the centimeter square on the bottom cancel out. So our answer is 9.405 centimeters, 9.405 triangles. So it's a coincidence that the number of triangles we'll need is the area of one of the triangles. The only reason why this happened is because we happen to have 14 triangles, which was the area of one triangle. Now I also want to point out that the units canceled out when we divided the areas by each other. The reason why is because if the units didn't cancel out and we had 9.405 centimeters, that's not a number, that's a length. So this answer says that we need this many triangles worth of area to build the whole flash drive. So we can't have it in centimeters. That's why we made sure that our units canceled out. Does that make sense, everyone?
Yes, sir.
Very good. Thank you, Miss Ariel. It's a good problem.
Okay, sir.
Sir, I have a question about one thing, like how to, like, how do you find all the triangles inside of the shape? That's the thing I can't understand.
Oh, that's fine, Mr. Aryan. What we said when we made our little model here is that we said, let's say that all of these squares are the same. And since all the squares are the same, all these triangles are just cutting the square in half. So because all the triangles are cutting the square in half and all the squares are the same, that means all the triangles should be the same by what we said when we made our little model here. And just to run through the exercise to give a good example, I said, instead of saying that the height and base was the whole flash drive, let's say the height and base is just the triangle. That way the problem makes a little bit more sense, the model. So we said that our height and our base, which Miss Ariel started us off with, by saying our base was 3.3 centimeters and our height was 5.7 centimeters, wherever it is. We said, okay, our triangle will have this height and base, which is what we started off with. Does that make sense?
Yes, sir.
Okay. So as long as you can say that everything in this model is the same, all the triangles and the squares, you don't have to worry about finding every single little triangle, because if you find one, you know what all of them are. That's how we did our problem. Mr. Aryan, you're the one left. Would you like to share your screen? Okay. Mr. Aryan, your video is a little blurry. Would you like to describe your shape instead? Okay, I can see a little. So it looks like Mr. Aryan has a suitcase, but we're only really looking at the suitcase itself. We're not looking at the handle. So Mr. Aryan's suitcase is a rectangle. Mr. Aryan, what is your area?
So my area, the base of the shape is 7.5 and the height is 4 cm. So when I did the calculation, my area ends up to 15 centimeters.
And your height was 4?
Yes, sir.
Okay. So you have a rectangle, base of 7.5 and a height of 4. What is our area equation for a rectangle again?
Length times width.
Very good. Length times width, or in this case, base times height. So this came out to be 7.5 times 4 is 30. I think you accidentally halved it.
Sir, I divided instead of multiplied. That's why I have a different answer.
I see. Mr. Aryan, you accidentally used the area for a triangle.
Yes, sir.
That's perfectly fine. It happens. The area for our suitcase is a rectangle of length times width, which is 30. So we can either say we can use this area of 30, or we can use your original one. We can say that your suitcase was a triangle-shaped suitcase. Because you already have your calculations. Let's say you have a triangle-shaped suitcase. Length times width over 2, which comes out to 15. So base is 7.5 and a height of 4. This isn't that ridiculous because instead of saying a suitcase, we can say that this is an instrument case, and instrument cases are oftentimes triangle shaped. So let's say we have our case that is triangle shaped of base 7.5 and height of 4, so our area comes out to be 15. And we labeled our shape as such. So now that we have the area of our suitcase, how do we know how many triangles fit into the suitcase? Or how many triangles we need to make the area of the suitcase?
Sir, we need to multiply it by 15.
Multiply the 14.
I don't really know, sir, but I think we should multiply the 15 by the amount of triangles inside of the shape to find the entire amount.
Oh, okay, I see. So you did something similar to Miss Ariel. And it seems that you also use centimeters. So the area of our little triangles are 15 centimeters squared, and you have a rectangle that consists of, you said 20 triangles, so that means that this would be 10 squares. So 10 squares, 1, 2, 3, 4, 5. Okay, and each of these squares is cut in half. So you have 20 triangles, you said, yeah?
Yes, sir.
Okay, so we have 20 triangles. And we said that the area of one little triangle is 15 centimeters squared. So to find, let's rework our model a little bit. We need to say that these measurements describe the triangles. So we'll write our little height here and our little base here. This is why this step was important, to label your measurements, because that way we know what we're doing. So we label our height and our base for our little triangle. We said there are 20 triangles of 15 centimeters squared. So that means we multiply and it comes out to be 300 centimeters squared. So our total area equals 300 centimeters squared. Now, it stays centimeters squared because we took the original area of centimeters squared and we multiplied it by a quantity times 20 triangles. The 20 does not have any units because it is a number. It is saying how many there are. So that means the centimeters squared stays the same. So it is 300 centimeters squared of the area of the whole suitcase. Okay, so Mr. Aryan, now we have the area of the whole suitcase. And we said before that our area for one of the triangles in the example is 14 centimeters squared. So how do we find out how many of these triangles fit into this triangle?
So we multiply them?
Close, we divide them. Because what we're saying is what we had up here. To find out how much area total there is, we took the area of one triangle, which we found here, and we multiplied it by the number of triangles. That's what we did here. When we try to do it backwards, so we find out how many number of triangles there are of this, we have to have the total area and divide it by the area of one triangle, being this one. So what we do is that our answer will be 300 centimeters squared over 14 centimeters squared. And that will come out to 300 over 14. The centimeters squared cancel out, so our answer is 150 over 7 triangles. So I see that you did not quite understand how to finish the problem, which is perfectly fine. As long as, do you get it now?
Yes, sir. That's why I asked you when Miss Area was presenting. That's why I couldn't finish it all because I didn't understand.
Okay. I noticed that I didn't have my video spotlighted while I was doing the work. Can you understand what we did to find the number of triangles we needed?
Yes, sir.
Okay. Ms. Alicia, this is I missed you twice already. So I'm going to tell you right now that in the chat, this is the name of the YouTube channel, Ms. Alicia.
Okay, sir.
And Ms. Alicia, if you would like to privately message me your phone number, and if you have WhatsApp, so I can add you to the WhatsApp group.
Yes, sir.
Okay. So just chat it to me privately.
Okay.
Thank you, Mr. Arian. So this is how we did all our work. Ms. Alicia, did you do the homework?
Excuse me, sir. Yeah, last week I don't get to stay back because
Okay.
my low.
Okay, so you weren't able to really hear the homework. That's
Yes.
perfectly fine. What we did is that we took our own shapes. We made our own shapes from any shape that we could find in the house. We said what area it had, and we gave it measurements so we could prove that it had that much area. And we took a triangle that I gave everybody, and we took that triangle and we said that this is the amount of these triangles we need to come up with the area for our shapes that we made. Does that make sense?
Yes, sir.
Okay, so that's what it'll look like if you watch the recording again. But
Okay.
we already went through 3.
Okay.
So that was the homework. It is 1:45 right now. Okay. So last week, when we left off, we were talking about lines. Does everybody remember it? So everybody doesn't remember the lines. Okay. So we've been talking about geometry the whole time, and last week we were reviewing lines. There are 3 types of lines, if you remember. Would anybody like to remember what these lines are each called? Very well. So this top one, if you can tell, it has 2 arrows on both sides. Does anybody know what it means when you draw an arrow on a line? We did this when we were drawing our number lines.
Parallel?
Not quite. You're thinking of if the arrows are inside the lines. What does it mean if the arrows are on the end of the line?
I'm not sure, sir.
That's fine. So if you remember when we drew our number line, we drew our arrows on the ends to say that when we were counting, that the arrow points that it goes on for forever. So arrow means goes on forever.
Excuse me, sir.
Yes?
Could those arrows mean positive or negative or like higher or lower?
So that is what we would call a vector. So a vector describes a value with direction. So what this means is that depending on which direction the arrow points, will say whether or not it's positive or negative. The way we would apply this is if you remember, if you remember graphs, we draw at the end of our graphs arrows. What we say is that the arrow that points up forever is the y-axis. And for all the points that are above the x-axis, so from here upwards and here upwards, all of these have a positive y value. That's because it has direction. So if you also remember, if it's below the x-axis, it's a negative y value. If it's to the left of the y-axis, it's negative x value. And if it's to the right of the y-axis, it's positive x value. So that's what it means for a vector. If it points in a direction, it means that this is where it's going. So it has either a positive or negative value. Another way of thinking about this is a compass. Oftentimes, what will happen is that you will be given math problems where the x-axis points east, the y-axis points north, west, south, etc. So what we would say is that if you were traveling northeast at a certain speed, it would be a positive speed in the x direction and a positive speed in the y direction. If you were traveling negative speed in northeast, what it means is that you are traveling against northeast. So instead of going outwards, you're coming inwards from northeast. This means that you have a negative x speed and a negative y speed. That's what it means to have a vector. So if you are going negative speed in northeast, that means you're going positive speed in the southwest. Does this make sense to everyone?
Yes, sir.
Okay, so that's what it means for the arrows to say if it's positive or negative. As you can see up here, it is the same idea. A number line is just a graph that doesn't have a vertical line to go with it. So if you said that this was to the right, if you were to count numbers negatively to the right, that means you are counting numbers positively to the left. But this is generally what an arrow means, that it just goes on forever in the direction that you drew your line for. So that means that this line would go on to 4, 5, 6 forever in that way. And if it counts like this, it'll go on -4, -5, -6, etc. that way. That's what a line is. You will understand the greater significance of a line when you do higher level algebra and more into trigonometry, etc. Calculus. But for now, all you have to know is that in math, when you say line, you specifically mean that the line goes on forever in both directions. That's why it's called a number line. Oftentimes, people will get confused in real life and they'll say that these are lines just because they're straight. These are not lines. They are a subcategory of lines, but in math, this is what a line specifically means. Now, this is called a ray. Does anybody see the difference between the ray and the line?
One has a arrow at the end and one has a point.
Very good. There's a point at the end. This point is important because a point means any point in space. So this is a specific value, and what it's saying is that this is the beginning of the ray, and the ray points in a direction, and that's why there is a line here. If you want to put this in real terms, this is where the term ray of light or ray of sunshine. Ray of sunlight. Have all of you heard the term ray of sunlight?
Yes, sir.
So this is where the term came from, because a ray describes a beginning and it goes on forever. What do you, if the ray of sunlight describes sunlight moving in a ray, what do you think that this point will be? Mr. Nathan.
Sorry, sir, I couldn't hear what you said.
That's fine. So Mr. Nathan, this describes a ray. It means that the ray begins at this point and it goes on forever. This is where the term ray of sunlight comes from, because it is a ray that starts at a point and it goes on forever. If the ray is sunlight, so the sunlight goes on forever, where does the sunlight begin? What would this dot be?
The sun.
Very good. This would be the sun. So in ray of sunlight, a ray of sunlight describes light starting at the sun and being emitted into space. That's what a ray is. Miss Ariel, you're having difficulty. Okay. Just
Sir,
trying
can you
to.
no, the internet was bad.
Okay. So Miss Ariel, a ray of sunlight describes light being emitted from a point into space. We said that because it is a ray, that the point where the sunlight starts at is the sun. So in ray of sunlight, the ray describes the sun emitting light that goes on for forever. Does that make sense?
Yes, sir, I can hear you properly now.
Very good. This is how we would apply a ray in real life. Another way we would apply it is time. Time is the most popular way of using a ray. So in time, what we do is that when we make graphs, we start at year 0. So we say that this is our graph. In our graph, as you can see, we have our y-axis and our x-axis here. If we say the y-axis is population, and our x is time, what this ray is saying is that the x-axis is a ray that describes time that begins at this point, which we will say is year 0 because it is at the origin. Because this is year 0, we now measure time by counting an amount of time from this point. So year 1, year 2, year 3, year 4, year 5. In reality, this can be any point in time. This could be 2001, and we count by year. So this is 2002, 2003, 2004. But what this is describing is a ray, where the beginning of the ray is when we start taking data. So this is year 0 in our data. In the y-axis, the ray describes our population. So this describes our population at 0, and it measures the population forever. So these are the values which we measure population by. What we will measure the ray with is that we will start from year 0. We will say at year 0, there's a certain amount of population. And from that population, as time goes on, the population changes by a certain way. But this is a curve that goes on forever because time goes on forever, and we say that this is a ray that begins at a point on the y-axis because this describes time. Does that make sense?
Yes, sir.
Okay. This is what functions are. And this is what you will expand to calculus about. This is what you're going to be using for most of the time. That would be Miss Ariel. It seems that both Miss Ariel and Mr. Aryan are having issues. in calculus, that would be Mr. Aryan. In calculus,
The internet was off just now.
that's fine. What we said is that the ray will describe our functions most of the time. In calculus, your x and y axi are lines. In the context of time and population, the point of these, the negatives, would be to describe time. In this instance, where we said y was population and x was time. Okay, Mr. Aryan. So in calculus, when we draw our graphs and we use lines for our axi, what we are saying is that if y is our population, x is time, so we had a population that we started with, and over time it changed like this. If year 0 is the x, is the origin at the year 0, what would the negative x-axis describe? If we were to count by years, so that year 1, year 2, year 3, this was year 1, year 2, year 3, and we started off at 2001, what could we say that the negative x-axis describes? Maybe Miss Alicia. If our x-axis is time and we start off at year 0 is 2001, so this is year 1, so this would be 2002, what would it be if we went to year -1?
Actually, sir, I don't know.
That's fine. Miss Alicia.
1998?
Close, close. You have the right idea. So year 0 is 2001. This is this. So if we counted back 1 year, this would be 2000. So you have the right idea. So in calculus, when we use lines for our graphs, if we would normally say using array that this was year 1 and we counted years in the future, if we counted in an x-axis, we would count years in the past. So this would be 2000, 1999, and 1998. So what this means is that if we were to complete our graph, and we said that this is what our graph looks like, we would say that if we started out with this population, based on what we have, we would say that at year -1, the population would be at this value, and at year -2, the population would be at this value, and so forth. Does that make sense to everyone? Okay. Does anyone have any questions? Very good. What we will do is that since it is 2:05, we will take a 5-minute break until 2:10, all right? Yes? Can anyone hear me?
Yes, sir.
Okay.
Yes, sir.
Okay, so we will take a 5 or so minute break until 2, 11, about. Okay, it seems that we lost Miss Alicia and Miss Ariel. Mr. Nathan and Mr. Aryan, can you hear me proper?
Not quite, sir.
Okay. Mr. Aryan?
Yes, sir, I could hear you.
Okay. What I will do is, since there is issue, I was planning on reviewing for after lines, I was planning on reviewing just all of our lessons of geometry. Miss Ariel. So what I was saying is that since we are having issues and for the rest of the class, after going over lines, I was planning on just reviewing geometry and giving homework that soon, if we find ourselves finishing lines early, we can end our class early.
Okay, sir.
Because we went over plenty today. So, what this tells us is that the y-axis and the x-axis, the functions not only tell us what we can predict in the future, but it can also predict functions in the past. So if we said that instead of this, our function started off here, so that our function was a certain value, let's say if this is our starting population and we were to measure only by not the population number, but by the growth of the population, we would say that our starting population is 0, and we would measure the amount of new people over time. What this would do is that at year 1, let's say we had 60, this is how much the population grew by. But in the past, it could also describe how much the population grew from previous years. So what this means is that if we started our graph at this time at year 2, and we said that this was our starting population, we could adjust our graph accordingly. So we would start here. For a study like population, it might not be useful because you generally want to predict what the population will be in the future. But if you were, say, an environmental scientist or an archaeologist, what you can do is that you can take readings that you collect over time, and using these readings, you can say, this is how, let's say, a population grew over time. So we could predict how much a population was back here. Or what you could say is that this is how much of a certain plant life there is, or at what altitude a certain land might be if the land was slowly sinking or rising over time. This happens in such like mountains. Or because of global warming, they're predicting how much the ocean would rise, and they predicted over time, this is how much we predict the ocean will be at this point in time. Or an archaeologist would look at remains. There's Miss Alicia. Miss Alicia, we said that we would probably end this class a little bit early after the lines. What we said is that we can use the graph to predict things in the future and things in the past. So we could predict, let's say if we were predicting how much the ocean would rise, we would take the amount of data we have, and we would say that we can predict in the future what the ocean level would be. Or if we were an archaeologist, we could take what we have currently And we could say, if this is what's happening now, we can predict what used to happen so that we know that 10,000 years ago, this is what the ocean level would have been back then. That sort of thing. People use this to measure water levels, and they use it to measure fossil records. This is how archaeologists tell how long ago dinosaurs probably lived, because they take the data that they have about soil in layers in the ground. They said that from what we found in the soil layer, we said that based on how deep you go, let's say X is time and Y is depth, that over time the ground raises by a certain amount that we measure in the ground. So we say that if we go this deep, that it would be this amount of time. Or this would be predicting how long it would be until the ground raises to this height. We could say that if the ground we dug this deep, if this was surface level, we would say that it would be this many years in the past that this ground would be. And if we were to predict how long it would take before the ground would raise up to this level, it would be at this time that the ground would raise to that much. Does that make sense to everyone?
Yes, sir.
Okay, that is how we apply lines to our graphs. And it's the difference between lines and rays, because lines in calculus we can use to say that we can measure the past using lines in our functions. With rays, we are concerned only with what our start is and further on. So that's what'll be the difference in statistical studies. So some graphs will be just the first quadrant, and other graphs will be all 4 quadrants. Finally, we have a line segment. Does anybody know what the difference between this line segment and the ray? What's the difference between these two? Miss Ariel, can you see a difference between this ray and this line segment?
Sir, one has a point and the other one has an arrow.
Yes.
The 2 bottom ones have 2 points and the top one has 1 point and 1 arrow.
Very good. So this line segment only has points, single points in space, and it draws a line between them. So this is called a line segment. This is where the term segment comes from usually. So when we split up things like movies, we could say that a movie takes a certain amount of time. So this is the start of the movie at 0, and this is 1.5 hours. One example of this is a YouTube video. We say that the YouTube video starts at 0 and ends at 1.5 hours. This is how the time wheel works. It's just a line segment. So you should generally understand how these work. They're just lines of a certain length. And if you break them into segments, That means that these little segments are length of this much. This is when the YouTube video has these little marks in here, and if you hover over them, they say that this is what the segment is titled. That's where the term segment comes from. The way that we would describe a segment in math is that it is the length of a line that extends from one point to another. So in a number line, you could see that each number we describe with a little tack. That's because each number is a point. That's why we said before, when we multiply an area times a number, the number does not have units because the number is a point. It does not have a length. So points are different from lines in that sense. Now the word point is similar to how you would usually say point. If you were to point in a direction, what it describes is that you have multiple points in a line. So because the line is built up of a bunch of little points, like how we describe our number line, what it means to point in a direction is that you have multiple points extending in that direction. So that's what it means to point. But a point by itself does not have direction. That's why the word we use is points versus to just point. Because a point does not have direction, that means that it has zero direction. As opposed to a line which has one direction. A shape like a circle, or if we go back to using a graph, it has two directions. And that's what describes dimensions. That's the difference between a point and a line segment. The reason why I bring this up now is because a line segment in terms of a number line, if you were to draw a line segment between 0 and 1, this does not describe 1. It describes one unit. If you draw a line between 0 and 1, it describes 1 unit. If it was just the point at 1, it would just be 1. The reason why is because a line segment between 0 and 1 has one dimension or one direction. That's why we say centimeters or centimeters squared, because an area of 13 centimeters squared, it points in two directions. And that's where this 2 comes from. In one dimension, centimeters, so we say one dimension of this line segment is 1 centimeter. It is 1 centimeter to the power of 1, and that means it's just centimeter. But this 1 describes one dimension or one direction. So that means it is 1 unit pointing in this direction. When we say 13 centimeters squared, it is 2 directions. So that means it is 13 split into pointing 2 different ways. The way we describe it is that 13 centimeters squared means a square of area 13. So since a square is a side squared, that means that it is a square root of 13 pointing in one direction and a square root of 13 pointing in a different direction. So this is where the 2 directions come from. That is how we describe 13 centimeters squared in this context. It is 13 centimeters pointing in this direction, square root of 13 centimeters, and square root of 13 centimeters pointing in this direction. That is how directions work, and we can derive this from understanding how lines work. And when we compare how lines work to a single point, we can understand then how a two-directional shape works by comparing it to a line. And when we compare a two-directional shape to a one-directional shape like a line, we can then compare these two to understand the difference between a three-directional shape to a two-dimensional shape. Does anybody know what a three-directional shape is? Very well. So if we were to say three-directional, and we were to say a certain measurement of three directions, we would say centimeters to the power of 3. What is another word for to the power of 3? We call it cubed. When we power it to the 3, so centimeters to the power of 3, we call it centimeters cubed. The reason why is because the same way that we describe centimeters squared by a square of area 13 centimeters squared in this instance, we can describe, let's say, 2 centimeters cubed by saying a cube of volume, not area, volume 2 centimeters cubed. So this would be 2 centimeters pointing in one direction, two direction, and three direction. This is how three-dimensional shapes work. And that is the point of going over lines. Does anybody have any questions?
No, sir.
Okay. So for your homework, what I want you to do is I want you to look through your notes and make sure that you have everything that we've reviewed so far. And if you'd like to, you can send a picture of your notes to me so that I make sure you have everything and you understand everything going on. Does that sound good?
Yes, sir.
Yes, sir.
Okay. Any last questions before we leave off?
No, sir.
Okay, so our meeting is done and all of you can go now.